Okay, so this week we're going to do, again, it's the practical data science applications, but we're actually going to do a regression this time rather than class predictions. This is kind of going all the way back to week 5 and expanding some of that work in the context of what we've learned over the last 3 or 4 weeks. And we're actually going to use a set. Now, Microsoft used to have a set of data science training on edX, and they had a capstone course where you had to do what you're doing in this project in analyzing a real world data set and do predictions from it. And this was the data set associated with that capstone. And the idea is that we're actually trying to predict for different kind of zip codes. We're trying to predict kind of rates of heart disease. So this is kind of almost an epidemiology application, so a little bit different from some of ours, but I think it's just a generally nice, interesting regression data set. So we have lots of data here. We have a lot of info, and this is at the county level, so we're predicting per county. So we have information about how urban or rural the county is. We have some economic indicators such as unemployment and the type of occupation. And we also have a range of, health indicators that we feel may be actually related to this, issue. If you have, obesity, smoking, drinking, etc. And then we kind of have some very general, age, ethnic group, college, non-college, level of education, birth rate, demographic indicators. So let's get to the data set. So we'll start off and we'll just load all the libraries we require. You've come across Carre before. We also go building some decision trees, but this time for regression rather than classification. And we need this library called GLMNet for a specific type of regression called logistic regression, which we're going to run later. So we're going to roadrun it in. Now, there's a lot of things like the area are all kind of all categorical variables. So we don't want to do it manually. We want to load them in as factors. And now let's have a look at the data set. Now, there's some useless information. We're not going to predict anything from the row ID. Then you see we have these kind of areas. We have our economics, and then we have all the other indicators that I mentioned before. We also have a little bit of missing data. Okay, so let's go back to that. So we remove, and remember, by setting any column to null, you just remove the column. Now, when R converts to factors, it automatically converts the levels, and it usually does it by alphabetical order. So what we want to actually make sure we do is we're going to actually put them in size order here. So we're going to set the levels to be first. We start off with the biggest metros, then we get to, we're also going to have rural, and then we're going to have the non-metros. So we're just going to set the levels in an ordering that we like. And it doesn't really matter. This is just for cleanness. So we have all the metros together. We have all the non-metros together. And again, we're going to do something similar with the heart disease. Sorry, the urban influence. So we kind of have two measures of how urban our area is. And let's do a little table here. And you can see that these guys are very, it's hard to do a full table here. But you can see these guys are pretty strongly related. So, for example, you see the metro million, large metro million. It's basically the same thing. So we might actually, thinking about this, if we put both of these guys in a regression model, we might going to have some multicollinearity problems. So, and also what we're going to do is we're actually going to change some of the names to make them shorter, which is going to make it easier for our graphics later on. So you see here, we have some very, very long names. And we're just going to change a few of those to actually, we're gonna use them for graphics and stuff. So there's just a few of those that I want to change. So here all we're doing is we're now going to make some of these a little bit shorter, some of our column names. So we look at this has got a longer column name, so we're just going to call it econ topology. And this is just because we're going to use this column in graphics later on. Now you look at the levels. These are kind of just overly long, federal, state, government dependent. So we're just going to change this to government dependent. And again, we're making the levels slightly shorter so we can do graphics easier. And what was I doing here? Yeah, so we actually make this, it was incredibly short and long, but we just kind of remove a few words from that to make it a tiny bit shorter. Okay, so let's now do a little bit of exploratory data analysis. So let's just look at the economic topology. Let's just do a simple ggplot kind of box plot. Our X is our econ topology, so that's what we're doing the categories across. Our Y is our heart disease, which is our dependent variable, and we're also going to fill by topology. So it's doing a very simple box plot. We're just going to make the title a little bit bigger, though, to make it look prettier. And here we go. And you can see here that depending on the economic typology of the area, you see where it's mainly a recreation area. I'm guessing kind of places out in Boulder, Colorado or somewhere with fit, healthier people tends to have lower heart rates. And we've got the manufacturing, mining, the traditional blue collars, a little bit higher there. That doesn't tell us a huge amount of information. And let's just have a look, but let's just do it by the general area we're looking at, the area RUCC. And interestingly, we've not tested this statistically at the moment, but we see that in the metros tend to have lower heart disease rates. And maybe this is just better healthcare, bigger concentration of educated professionals rather than some of the kind of the non-metro areas. But again, it's not overly significant. Okay, so you remember from chapter 5 we had G.G. Galley. And let's just have a look at some of the continuous variables and see if they're actually correlated. Okay, so now we're going to look at these continuous variables, and this is kind of almost a precursor to regression, where we're looking at some of the correlations between the variables. And I might just stop the video because this sometimes takes a couple of minutes. Okay, so it only took like 20-30 seconds. So here we could see the actual kind of the distribution of the different variables. And you see the air pollution particulate. Well, that's the interesting distribution. It's certainly not normal. But more importantly, we can see the scatter plots. We can actually see the correlation. So this first thing, the first row and the first column is the adult obesity. And the last column is the heart disease mortality. Now, we can't kind of quite see these. We've run out of space a little bit. But we can see, number 1 is obesity. Number 2 is smoking. So let's just have a look at the heart disease mortality. It's positively correlated with obesity, positively with smoking, positively with diabetes, positively with low percentage people with low birth weight, negatively correlated with excessive drinking. Now, that doesn't seem to make sense because excessive drinking would make it unhealthy, but maybe it's like the more upper class urban areas where everybody's drinking their wine and their spirits, and generally they're pretty healthy, but they have secret drink problems. I don't know. But excessive drinking is a negative correlation. Physical inactivity is a positive correlation. And the particulates kind of pollution measure of pollution is also a positive correlation. Okay, so let's just remember DevOff just clears our graphics. And we're just going to show this in a slightly different way. We're going to actually do something called a correlation plot. And the correlation plot just kind of colors by the level of the correlation. So it's like almost, I'm going to use a library core plot. And we're basically going to create the correlations using the core function. So let's just do that. And the complete ops, this just says, you know, if you only have some of the information available, do you still do the correlations? We have a pretty good data set here. We'd have missing data, so we'll just stick with complete observations. These are just the 22 to 32, 34. These are just the continuous columns, and obviously I'll show you what they are in a minute. So let's just plot the correlations. And remember that perfectly correlated variables have a correlation of 1, and perfectly negative correlated variables have a correlation of -1. And 0 means there's absolutely no correlation. So each variable is kind of correlated with itself. Let's make this a little bit bigger. And again, you can see these kind of ideas. The heart disease mortality is positively correlated with everything except excess drinking, which is kind of a reddy-orange color. And you can see a lot of these health factors are correlated with one another. Like things like diabetes and obesity are heavily correlated. Diabetes and smoking are heavily correlated. So again, this might be some issues with multicollinearity when we get to our regression. Okay, let's just coax my code window back. And this, we just said, this just has the circle method, i.e. we've drawn circles, so we could do a complete color plot. And here it's exactly the same again, but this time, and we've actually, because we have more room here, because it's pretty small, we've actually given some more variables here. So we've got some of the ethnic variables here, we've got some of the economic variables here, and we can see, see correlations between these. So civilian, employment is strongly negatively correlated with unemployment. We kind of know that. And heart disease negatively correlated with labor, strongly correlated with moderately correlated with unemployment, which I guess we kind of know. If people are relatively high unemployment, we're more likely to have poverty, and we're more likely to have health factors leading to heart disease. Now, the data at the moment, there's a little bit of missing data. But what we're going to do is we're going to use something called imputation to get rid of the missing data. Now, I actually put this in the notes, so I won't write this out, but I'll just go over the notes. And I just talked about the different types of imputation or redoing missing data. So we can just replace with the mean or the median or the mode, the common value, mode if it's categorical. But there could be issues, so imagine this is on movie viewing behavior. And I really love chick flicks, but I really hate horror movies. And so I give like 10 out of 10 for horror movies, and I give 2 out of 10 for, so I give 10 out of 10 for chick flicks, and or like The Notebook, and 1 out of 10 for horror movies. The average for a new horror movie is 7 out of 10. So I'm given 7 out of 10 for the horror movie. But that isn't very realistic given my preferences. So there are limits to this mean imputation. It changes it biases the data set and changes the variance. This is the k-nearest neighbors approach, which I talked about in last week's note, i.e. we're looking for, based on shared features, we're looking for similar items with low distance between us and them, but who have actually got the missing data. So we find somebody or something similar based on our shared attributes. We look at the data distances. That's why it's called k-nearest neighbors, a little bit like k-nearest neighbors classification. And then we find, and then we actually find these close neighbors based on the shared attributes, and then we just, what they have and we don't have, we can transfer over. Now, statistical imputation, going into this statistically is a little bit beyond this class, but we assume the observations are from a joint distribution across variables, and we basically create this distribution and then we sample from this distribution. Now, if we have single imputation, we take one sample. There is sometimes an issue is if we have random error, that's sometimes biased results. So what could we do? Well, we actually can sometimes take multiple data sets and then multiple imputations to then aggregate the results. For this time, we're just going to use a single imputation just for ease. We don't want to do like 10 different regressions. So for imputation, we use the mice library. And basically, we build our imputation model, our data distribution model, using the mice function, and then we use the complete function to create the new imputed data. So I'm just going to run that, and then I'll pause the video. This will take about at least a few minutes. Okay, so and yeah, while it was actually running, I created some new code just to check the missing data. Which is just gonna, I'll actually put this in the notes. I think this is actually quite useful. And we can see that there's no missing data on this new data set. Okay, so let's do our regression and see which parameters are actually important. So let's just kind of build a regression model. We're doing the usual, using the LM. The heart disease mortality is the dependent variable, and all my independent variables included, and it's heart disease too. So let's just have a look at this. It's quite a big regression model, so let's make this a little bit larger. Let's just run it again. And there, we got everything on the same column. So we can see here, generally, you see they're not very significant. We have negative estimates for the first area category. For the metros, we have a significant for the metros. I'm guessing because it's not included, the metro over 1 million is the base category. So everything is relative to that. The same here. So everything here is relative to that base category of over 1 million, but there's not a high degree of significance there. The same with kind of urban influence. You can see the micropolitan just adjacent to the metro is lower than the big metro, but the non-core is larger. So this is maybe like more of an industrial area. So remember, when you're doing regression, you've got to think what the base category is and what you're doing relative to it. And the same with the econ typology. And then let's just look at some of the continuous variable. Some of these measures, like % insured adults, is significantly positive. Age 65 and older is negative. Now, you'd maybe think that was actually, weirdly, older people are more likely to get heart disease, but I think it's just, the demographics where people don't live quite as long tend to have higher rates of heart disease. And you see if you're Native American, high degree of Native American, that's going to be people in the ZIP, that's going to be negative. And both African American, Hispanic white, and also Hispanic tend to be positively related to kind of heart disease. And then things like, obesity is positive, diabetes, low birth weight. And in this model, actually, the excessive drinking is positive. So that's switch signs. That may be due to multicollinearity. And again, some of these are probably not direct things, but just associated with the neighborhoods. Like areas with high homicides are significantly, higher heart disease, and areas with higher vehicle crashes. If you have a poorer area with more homicides, more vehicle crashes, then that just has to be that's issued. And then, of course, the year of birth is highly negative. So if you're born in like 90, I think that's the average year of birth. I'm not sure. But that's highly negative. Okay, so there may be some issues with this. Let's just do the check we did in Chapter 5 for multicollinearity. Remember, we look at OLSRR. And I had to do some options because there's so many variables to print all the variables. And we're going to use the OLS VIF tolerance function. And you see we have some infinite values. And in fact, for all of these metro values, they're all infinite. Now, why is this? Well, it's because these two variables are just we saw when we did the table, they're very strongly related to each other. So let's remove these. And also you'll find some of the ethnic groups are also got a very high degree of multicollinearity. You see here, this is like 40 and this is like 20, so they're all above 10, not quite as strong as before. And so we basically, that's because they all add up to 100, so you can calculate one ethnic group from if you have all the others. So let's just set the non-Hispanic white to be 0. So we create a new data set and we're basically removing the problem columns. So let's now run this regression on the new data set. And you can see this is a little bit better. You see you get a bit more significance. We still missed, the base is the metro greater than 1 million, but we see a little bit of significance in the small metro and adjacent to metro as before. Small metro has less heart disease. This the micropolitan area and the non-core have positive. Then we have the different economic typologies. I can't remember what the base was, but relative to the base, manufacturing is positive, and mining is positive, and non-specialized is positive. So we can see here that I think the base is probably something like, something white collar. And again, I won't go all through these again because it's pretty much the same as before. But you can see the heart disease here is we have interesting, and we have the areas Hispanic, non-Hispanic, African American, and Native American all have kind of negative coefficients, but the Asian demo with higher percentage Asian does have positive heart disease. Now, it could be due to various factors where different people live, kind of in the US, so it's hard to make direct associations there. But now let's test for multicollinearity. And let's just look at our R squared at the moment. This is interesting. We have an R squared of about 0.69, and we have an adjusted R squared of 0.8676. So we can actually run a stepwise. So again, this is exactly what we did in Chapter 5. We built a base model, which was like just the intercept. We built a full model. And then we just kind of went through to the full model, adding variables based on this model fit we called the AIC, or adjusted R squared, until the model, the model accounting for the number of variables gets no better. So let's run this and I'll pause the video again. Okay, so that literally took 5 seconds, so I didn't need to pause the video. And you'll see we didn't really change the R squared much, but we have cleaned out some of these non-significant variables. Now, this is actually a pretty decent, predictor. Why is it not perfect? Now, I've got a bit of inference about this. So this is a map of the US, and this is the rate of heart disease. And you can see it's pretty actually regional. Okay, so this is the level of heart disease. And you can see there's this pretty strong belt across the US where we have a high level of heart disease here. And this is sometimes called the stroke belt. You go from East Texas through the south, then kind of up through West Virginia, Kentucky, and these all have very high rates of heart disease. And you could actually look by ethnicity, so you could look by African American. Okay, give it a second. It's a little bit slow this morning. And you see here some of these there's insufficient data in some of the metros, but you can see generally where there is data, relatively high kind of heart disease. And we can look at white, non-Hispanic. And you can see relatively high heart disease in some areas, but not in others, and particularly kind of centered in the south. And what's interesting here, if you go down into Oktibbeha County, it's basically lower than anywhere else in Mississippi. So Oktibbeha has the lowest in Mississippi. But I thought that was kind of pretty interesting when you relate our little county here to the rest of Mississippi. And this sort of practice of looking at things like, you know, social patterns, socioeconomic data, demographic data, and relating it to health outcomes, I said again, is called epidemiology. I did put a few, I won't go through them, but in a few links in the notes, I did give some interest in epidemiology. If there's anybody interested in that area, you do require a lot of statistical knowledge. In a way, it's similar to what a data analyst or a data scientist does, but you're kind of, rather than helping companies make profit, you're kind of doing it for the good of community. But if you look at the wages here, the wages for an epidemiologist tend to be lower than for a data scientist. But I thought, just kind of, I'm guessing most people in this class aren't that interested, but I did include those links in the notes, which I just thought was interesting. Okay, so now let's go to we've built the basic models, we've gone over the data sets. Now in the next video, we'll start looking at kind of building some tree models.